Hey, hello, welcome to my real-time architecture using Hadoop and Storm talk. I am Nathan Marz. I am your speaker today. I work as a big data consultant for data crunchers, and I've always been really interested in big data, Hadoop. I've done quite a lot of projects using Hadoop and lately Storm. And I have a little background in PHP, but don't tell anyone. So just to give some context, I'll just introduce you to the 3 V's of big data. I guess most of you have heard of it. So I guess there's about, well, the volume of data is rising. There's more and more data. And I guess in the future, let's say in 2015, we estimate that there will be over 15 zettabytes of data, and the rise of data it's rising fast. So you will have so the speed of which we accumulate data is ever increasing, and where in the past we used to throw away a lot of data and a lot of insight, we are keeping it much more and more. And then there's, of course, the velocity of data. We generate more and more data, and it's coming in at a higher and higher rate. So especially with the Internet of Things and so on. But the velocity of data is really important because if you want to make decisions based on your data, well, almost any decision taking is a time-sensitive process, especially in fraud detection. You want to catch them before while the transaction is happening, not afterwards, for energy allocations, marketing campaigns, stock market transactions, and so on and so on. And then there's the variety. While in the past, we mostly dealt with structured data in relational database systems. But if you only deal with structured data, you're ignoring a whole lot of data that actually exists within your organization, exists somewhere. But it's a bit like ignoring 80% of the truth out there and just focusing on what you need. So if you only have a BI tool, everything will look like a nail. And so what kind of unstructured or semi-structured data is there? I'm thinking about Word documents, emails, but it could be photos, video streams, or even API calls. Why not? But in the end, what we almost always want to do is to bring structure to this unstructured data. So, while in the past, if we look at computing trends, in the past, computing was, like CPUs were really expensive, disk storage was expensive, memory was expensive, but coordination, especially inter-process coordination, was really easy. Because, well, in the past it was mostly about single-threaded applications, while our current situation is a lot different. Computing really has become cheap. We have multi-core CPUs, as well as something like the Amazon or Azure clouds, where you can get easily a lot of CPUs and a lot of compute nodes for not that much money. Disk storage has really become really cheap. I mean, you can get a 4 terabyte hard drive for under 80 euros. Memory is becoming cheaper and cheaper, especially if you view an SSD drive as well as an extension to your memory. But coordination has become a lot harder because, yeah, if you're doing multi-threaded programming, one way is to deal with locking and so on. So there's a lot of opportunity for lost computing. So while one process is waiting on some resources. But there are ways to solve that. But coordination really has become a lot harder. A lot of what I'm going to talk to you about now are actually the ideas of Nathan Marz. He's an engineer that, well, he was an engineer at Backtype and Twitter, and he's now creating his own startup in stealth mode. I don't really know what it is. I'm curious, so if anyone knows, tweet about it or something. And he also wrote the Storm, Storm processor, as well as Cascalog, which is based on cascading, and ElephantDB. So what I'm going to talk to you about now is a data system. And in a data system, so let's first define what data is. Data is actually a lot more than just information. And not all information is equal. Because once you go, if you start digging deeper, a lot of information is actually derived from other pieces of information. So, for example, if I look at the number of followers on Twitter, which is actually all the follows and unfollows that ever happened combined, or if I look at if I log into my bank website, my account balance, what I see at my overview, is actually the combination, is actually the result of all previous transactions that ever happened on my account since I started it. So once you start digging deeper, eventually you will find the most raw form of information. And this is, let's call this data. And it's really similar to an event. So, and this event, or data, we simply hold it true because we can't really dig deeper. And this means that in an ever-changing world, we finally found some stability that we can base the rest of our system on. And as you probably, and everything we do can probably, everything we do does generate events, and it generates more and more. If you go to a supermarket nowadays, they have some cameras that monitor your every move. So if you look at product X and you then look down, it's probably going to be measured. So it will be always all kinds of different events. So even as well, yeah. If you drive a car, you will. What I heard was that the Tesla car, or no, the Google car, generated about 4 gigabytes of data a second, which is, well, cool. But we have to do something with this data. If we're just going to keep it, it isn't really interesting. And while in the past, events used to manipulate the master data, today, events are the master data. And that's really an important shift from the past. So let's store all those events, or let's store all the data. And it has become a lot easier because it's much more cost effective. Often it's a lot more expensive to filter the data beforehand, before storing it, especially because the disk space has become quite cheap, really cheap. And data or events are immutable. And this is really an essential property. We're going from a CRUD world, create, read, update, delete, to just a create and read world. So, of course, the information that we're going to use, it might change, but the underlying events or data doesn't. And there's a strong parallel with functional programming there. And because it's immutable, it's much more tolerant to data loss, or human error, hardware failure, or data corruption. So they're all nice properties. And this data is, of course, time-based. And it's obviously because for an event to be true, an event needs to be always true, but it will only be true on a certain timescale. And if you're going to keep the data, the time with each event, we can always regenerate our state of a specific moment in the past. So I can always go back and ask, what was my bank balance on the 1st of May in 2005, or something like that. So in traditional systems, how do we capture change? If, let's say, I move from Antwerp to Ghent, in a traditional system, it would be an update. While in this new system, it would just be a new record. And of course, but this data, we need, of course, this data, most of the time we're not really interested in this raw form, we're not really interested in the raw events. We're mostly interested in the derived information. So and our information is mostly based, we can say that our information is a query, which is actually a pure function that takes all data as the input and generates a view. Of course, different functions might look at different portions of the data and aggregate the information in different ways, but it's always just a generation of the data. So let's say I'm interested in the number of people living in each city. I would go from, I would start with a list of all events. I would use a process that went over all these events and used some kind of that goes over all these events and processes them and filters out the most relevant, the current ones, and then does some summing and counting. But this is often going to be slow. So we have all our data and we have our query, but if we want to use our queries, it's going to be too slow. So we're probably going to pre-compute our views, especially if you have lots of events. Let's say we have billions of events, millions or billions of events, or petabytes of data, or terabytes. We're not going to be able to answer a query in real time. Not even with something like Drill or Impala. So what I'm proposing is a layered architecture with a batch layer, with a speed layer, and with a serving layer. So another view of this architecture would be one or more streams of incoming data that's getting processed and written to Hadoop in our batch layer. The batch layer will store the master data set. And it will be written as well to a speed layer. And we're probably going to use some stream processing on top of it. So something like Storm or Akka might be a good fit. And then we're going to recombine the data of the output of both layers using a query layer. So let me talk a bit about the batch layer. So just for the reference, we have our incoming data, and we're now going to talk about our batch layer. And some essential properties of the batch layer are unrestrained computation. So in your batch layer, you can calculate anything, but it might take a long time. And there's no need to denormalize your data. You can store everything normalized. Of course, the views you're going to generate, the data is often, if not always, not denormalized. Of course, it might be that you need to take some shortcuts in your batch layer, but as always with an architecture, it's there's a difference between the ideal and the and the actual output. And it's probably going to need to be horizontal scalable, because if you're going to store every event that's ever been generated, it needs, well, you need to have a clear upgrade path, because you will have more and more events. And the batch layer is, of course, high latency. So it will take our query the queries that we run on top of the batch layer will take a lot of time, but let's pretend that it doesn't really matter at the moment. And something really important in the batch layer, if you compute something, your input is immutable. So if you run the same function on top of your inputs, you will always generate the same output. So it's idempotent, which is a nice property, because then you can always restart your processes. So if anything goes wrong during the process, you can just restart it. You just throw out your intermediate results and just restart it. And your batch layer will store a master copy of your data set. So this is where your immutable data lives. And it's append only. We don't want to have mistakes, especially if you can do file updates. You always have a risk of you have to deal with locking and so on. So it's easier to just say data is write once, read many. And I think an excellent candidate for the batch layer is Hadoop, but it doesn't really have to be Hadoop. I think any kind of distributed file system combined with a processing framework might do. So I guess you could use something like Spark as well, or whatever you want to use. And in the batch layer, we're actually going to create views. So we have our master data set, and we're going to run some processing on top of it and generate views. In Hadoop, we're probably going to use MapReduce. So just a quick reminder what MapReduce is. We have a large data set. We will divide this in subparts. Then we will perform the same calculation on top of all those subparts. And then we will recombine the output of all those calculations. And this is MapReduce. A bit of another view on top of it is we have our inputs on our file system in HDFS. Then we have a map job that will read. Each map job will read a different part of your input data. The output of your map job, so let's say you have a word count. Every map job will output the word with its count. And then in the second step, you will have a sort and shuffle phase where the output of your map jobs is sorted, and if you, let's say, you're actually going to do a bit of a grouping, and it will be read by your reduce functions, and then your reducers will output again a file or to anything. So maybe a quick word about serializations and schemas. I think schemas are quite important. They give structural integrity. They guarantee on what can and can be stored, and they will prevent corruption. So you want to use schemas because you want to detect corruption at write time instead of at read time. It will be a lot harder to solve a read time corruption than to solve a write time corruption. If you know that your data isn't valid anymore at write time, you can probably recall your API calls or do some other escalations. If you do it at read time, you will have a lot of a hard time. And I think CSVs are actually a really bad format. I see a lot of people on Hadoop using CSVs, but there's a lot of value to be used with, if you look at something with a schema like Thrift or Avro or protocol buffers. It's a bit the same reason why why there's a big advantage of using, well, even it doesn't have to be CSVs. You don't want to store JSONs on top of HDFS because you want this strong guarantees about consistency. And there's a bit of a bonus because it will be a lot faster. The views you will generate using your batch layer will actually will only need to be read-only. They can be updated in batch, so there are no random writes, and each iteration of your batch process will just generate new views from scratch, and it will overwrite and replace every view that has previously been generated. So I think a few candidates for this batch views are something like ElephantDB, or Splout, or Voldemort with a read-only backend. Or why not use an Elasticsearch where you use a MapReduce process to write out your Lucene indexes, and you just read those Lucene indexes, and you output those using and you make it available using Elasticsearch or Solr. Why not? So, but we're not really done yet. So when all this data is written into the batch layer, it will always miss a gap of data because the batch layer will take some time to do processing. So this gap will just be the time that since the last time your MapReduce process fully run. So it will be just a few hours or maybe a few days of data. But if you're and to bridge this gap, we're going to use our speed layer to bridge this gap. In our speed layer, so just as a quick reminder, we just spoke about our ingestion and our batch layer, and we're now going to talk about our speed layer. And our speed layer is mostly based on stream processing. So especially if you have an incoming stream of tuples, a stream of events, it might make sense to do some stream processing on top of it. And you want to do some continuous computation. And it might be interesting. It doesn't have to be. Your stream processing might be transactional. It doesn't have to be, but it will make some calculations a lot easier. And essentially, your speed layer is just storing a really limited window of your data. So it's just to compensate for those last few hours of data that aren't yet ingested by your batch layer. So all this complexity of the speed layer is isolated in this part of the system. So And if anything goes wrong, it will be auto-corrected by our batch views. Because let's say a few machines crash or there's a miscalculation in our speed layer, we still have the raw events that we keep as our part of our master data set on top of in our batch layer. So we can always go back and regenerate the states. Or even better, it will always, the views of our speed layer will always get replaced by the data that's ingested in our batch views. So in our speed layer, we have a bit of a choice between availability and consistency. So the CAP theorem is, well, consistency is all nodes see the same data at the same time. Availability is that every request, will receive a response. And then you have your partitioning tolerance. So that means that your system continues to operate despite network loss or failures of part of the system. Partitioning tolerance is something you don't want to give up in any distributed system. So let's say if you look at the HBase, it's CP, consistent and partition tolerant, or Cassandra is available and partition tolerant. If it's AP, it will probably be eventually consistent. But you can't really sacrifice partitioning tolerance, because if you sacrifice it, only one part needs to break to have your whole system falling down. But then there's something like eventual accuracy. Because you're doing real-time computations, some algorithms will be much harder to implement. I'm thinking about, a simple example would be a unique count. You don't really, in this layer, you don't really have all the data, and it will be too much data to keep everything in memory. So, a unique count will be hard. So for those cases, we might just estimate results. Same goes for machine learning. You might create a model using your batch layer, and you might just apply your model in your speed layer. And your model will be auto-learning because every new event will get, because your model will get regenerated on every batch run, and you will continuously run your batch results. So if we look, this is a bit of a, in our speed layer, we're probably going to store some real-time views, because of course our end result, we want to read, because we want to read, we want to do something with the data. And you want to have a view on your data, so we're going to need to store it somewhere. But let's first talk a bit about the message about Storm. I think Storm is an excellent candidate for the speed layer, but it doesn't have to be Storm. I think something like Akka or Spark streaming might be interesting as well. But I think it's essential that you do some message passing, and ideally it should be distributed and horizontally scalable and fast. It's really data in motion. This is what the architecture of Storm really looks like. You have a Nimbus which manages the node, the cluster. Sorry, it's quite similar to the job tracker on HDFS, on Hadoop. Then you have your workers, which are machines. And on each worker will run one supervisor, which will manage the executors and tasks. And every executor is a physical GVM process. And within this JVM process, the actual tasks and the actual tasks will run in its own thread. And a task is actually a bolt or a spout that will process the data stream. So if you look a bit at the data model of Storm, we have a tuple, which is a named list of values, and it's dynamically typed. And then we have a stream, which is just a sequence of tuples. So we have our spout. A spout is actually the source of our data stream. It might be sometimes replayable. Doesn't have to be, but it's an interesting property if it is. And a bolt, it does actually do the stream transformations. And every bolt has at least one input stream and zero or more output streams. And in Storm, there's not something like a sink. So the bolts are, you can have a bolt that is responsible to communicate with other systems like APIs or a database or Cassandra or something like that. And an interesting feature of Storm is that you can use grouping. So one spout or bolt, so you can have multiple output streams, and a bolt can have multiple input streams and rejoin them in real time. And what you can do in your bolt is you can do some sliding window calculations and so on. So if we're looking at the data ingestion side, I think something like a queuing system like Kafka or Flume or one of the many MQs like RabbitMQ might do the job, is a good candidate for it. So we also have so in our speed layer, we are going to generate views. And those views need to be queryable, and we need to write them in real time. So it will be we are going to need a read and write database. And the logic behind such a database is much more complex than the logic behind something like ElephantDB. And the reason why that is, it's because it has to deal with updates and locking. So I think some candidates for our read and write databases are something like Cassandra, HBase, or Redis, or one of the SQL servers, or Elasticsearch or something. I think you can use any traditional SQL or NoSQL database. So then we have our serving layer. So we just generated views in our batch layer, our batch views, and we generated our speed views, and now we need something to combine those. So it will be a lot of random reads. The serving layer needs to be able to answer any question in a really short amount of time. So this layer will query the batch and real-time views and do a merge operation on top of it. Well, the easiest thing to do it is actually, if you are having, is to have in your batch layer, you will have all data on top of, besides the last couple of hours, and in your real-time layer, you will just have the last couple of hours of data. And so you could use some kind of coordination mechanism where you specify the offsets for which data should be read where, or you could use just based on the time. So in this serving layer, because you have to query two different kind of components, how do you query an average as a much simpler example? Well, if you're going to store two averages, yeah, you can't really combine those. So for an average, it would be, of course, you would store the sum and the count both in your speed and your batch layer, and you just recombine those in your serving layer. So your serving layer is quite important, and there will be a bit of logic involved there. So when I look at the overview of this architecture, we have our incoming data that's getting processed by our batch layer. It's written and processed as well to our speed layer, and then the output is merged by our serving or query layer. And actually this is quite similar to something like CQRS. So CQRS, command query responsibility segregation, applies this itself, where you have a different path for queries and commands. Commands are writing things or updating things, and query is a different path. So I think that CQRS and this architecture, well, actually, this architecture is just an implementation of the CQRS pattern. And I think one of the buffs, I think on Monday evening there was a buff about CQRS by Tom Michiels, so it might be interesting to look at it on Parlays. So there's the Lambda architecture. So this was what I just presented, was the Lambda architecture. And an essential property of the Lambda architecture is that it can disregard any view, batch or real time, and just recreate everything from the master data set. So it has a really high tolerance for human programmer mistakes, system engineer mistakes, as well as system errors. Because you can always recomputate your views. So if you have a bug in your view generation, and I don't believe developers who claim that they've never introduced a bug in production, but it matters a lot less because you can always regenerate your outputs. And your inputs, you don't change those. Once it's written, it can't be changed. Well, of course, there's always, for legal reasons, you might need to change some things, but the principle is that you shouldn't change what you've written so far. And the data storage can be highly optimized because your data storage, you can optimize your data storage independently from your query resolutions. So that's the reason why you generate views, and those views you will probably keep them in memory for faster and random access. But your data storage, all your raw events will be just kept on disk. And disk is a lot cheaper still than memory, and it will always be cheaper than memory. And immutability, well, I think because if you keep things immutable, well, it really makes a lot of things a lot easier. It will be easier to scale. It will be easier. Your fault tolerance will be much higher. So when you're designing your next system, you really should take a look at how you can make your system as immutable, how you can keep your master data set as immutable as possible. So I guess that was my presentation. Are there any questions yet? Yes.
Are they dropped and regenerated from scratch, or are they updated?
He asked if the views are regenerated every time, or just updated. Ideally, they should be dropped and swapped over ElephantDB will have support for that, as well as Sprout. They will both have support to just update your views and swap them over once it's done. Because if you're updating, then if there might be a bug in your view generation, and you already updated the part of your view, then things still go wrong. But that's for the batch views. For, of course, the real-time views, you will probably keep on updating them with some partitioning scheme. Are there other questions?
I've done a few event source systems, and from my point of view, the Lambda architecture seems like you could use it to hook maybe like data warehousing functionality up to an existing event source system. Is that something you would agree with, or?
No, I think so too. I think this might be another. You said that that the Lambda architecture might be a good addition to a data warehouse.
Yeah, if you have existing event source systems, right?
Yes.
And you want to have data warehouse functionality on the operational data from those systems. This could perhaps be a good fit for that kind of use case.
Yeah.
Yeah,
Okay.
you just subscribe to the events from the event source system, and you input that input to your Lambda architecture, and that allows you to redo batch projections without restarting the original system.
Yes. Yeah. So if you have an event sourcing system and you want to do some and you want to do some additional reporting on top of that, you want to do this architecture might be a good match, absolutely. And I think because it might you can slide this architecture very gradually in a lot of systems in, because it doesn't change the rest of your systems around it. As long as you have an input stream of, as long as you have the input stream of events, as long as that keeps on flowing in, you can always, it doesn't need, so it can just use, a message bus or a streaming system. So yeah, absolutely. And the output of your views could be a data warehouse. Why not? Are there any other questions? Okay.
What are the limits of the architecture?
What are the limits of the architecture? I think the limiting factor is if you really need something that's really real time. This architecture is near real time, and you can't do anything in your. You can't do any calculation. You can only do some calculations in your real time part. So if you want, like unique counts, you will be a lot harder. So it's most about the algorithms that you can use in your real time part. It might be that you will need to have too much data or all your events available in memory, and then that defeats a bit the purpose of this architecture. So, but you could use, it might be possible to use some estimations in your streaming layer. Like for instance, if you have a YouTube video, the counts on a YouTube, the number of people that viewed it, so it first will be written to a batch, to a speed layer, and once it's processed by, and actually the number of, once a video goes viral, it takes too long to really update it and to do a unique count for every video. So they will just increment the counter based on past performance into view. They will just show an incremental counter without that people have actually seen the video. So it can be, and of course, once you have the real data, you can replace your estimations with the data of with the output of your batch views. Okay. Are there any other? Yes.
Do you have some estimation about how long does the batch layer takes to recreate?
The question was, do you have some estimations about how long it will take for the batch layer to recreate a view? Well, that will depend on several factors about the size of your input data, the type of calculations, and of course, and the number of machines you have available. So I can't really say that it will take 2 hours, but ideally it should take less than a day. You should aim for that, to keep it less than a day, because the faster your batch layer can process all data, the faster it will output new views. So, and in your batch layer you can do anything, as long as, and the batch layer views are very correct, but a bit out of time. So if you can keep this time gap as small as possible, that would be ideal. So, but because it's horizontal scalable, if you really need to add some machines, you can always add some machines, especially if you use Hadoop, you can add some extra machines to do additional processing. Yes.
So if I understand correctly, you're saying that you're doing transformations in the batch view that you might not do in the speed view, right? It's not like an exact match between the speed view transformations and the batch view transformations.
Yes, just to repeat it, there's not, he asked is it an exact match between the batch and the speed layer of the transformation you're doing? And well, if you can use the same calculations in your batch and your speed layer, you're very lucky. But most of the time you can't. So for a simple counter, it will probably be the same. But yeah, for anything else than that, it will always be a bit differently. But if you want to reuse as much logic as possible, Twitter created something like scalding that uses where you can reuse large parts of your logic, as well as and if you take a look at Spark, you both have Spark streaming and Spark batch processing. So there you can reuse a lot more. But I don't. But because it's a bit of a different model, it's not. In most cases, it's not really possible and not really necessary to copy your logic. So you will have to do some additional tasks, and most probably you will have your speed layer. The calculations you do in your speed layer will be a bit simpler than the ones in your batch layer. Yes.
How would you deal with the iterative algorithms?
He asked, how would you deal with iterative algorithms? Well, good question. Well, there's no problem in your batch layer, so obviously, but yeah, in your speed layer, you will have to do some estimations, or what you could do, you could reuse. What you could do is you could output some state, some extra information in your batch views, and reuse this information that you just wrote, and reuse that information in your speed layer. But it's not, well, it's not ideal for that, because, well, mostly because you have so much data that it's, yeah, you will always have to compromise somewhere. Okay. Any other questions? Good. Thank you.